Hey everyone, and welcome. Today we are cracking open the user's guide to, well, the most complex machine we know of, your brain. We're going to get into the science of how you learn, how you remember, and how you can do it better. Let's dive right in.
So, have you ever had this happen? You can perfectly recall the lyrics to a song you haven't heard in a decade, but that really important number from this morning's meeting? Poof, gone. It feels totally random, doesn't it? But it's not. The answer is all about how your brain is built to make memories.
And to really get a grip on how memory works, we have to look at someone whose brain was missing a key piece of the puzzle. His story is one of the most famous in all of neuroscience, and it basically blew the doors off what we thought we knew about learning.
So let's talk about a brain without memory. This is the tale of Henry Molaison. Back in 1953, Henry had severe epilepsy. In a really drastic attempt to cure him, surgeons removed a part of his brain, including a little seahorse-shaped structure called the hippocampus. And hey, the surgery worked. His seizures got better. But it came at a shocking price. Henry lost the ability to form any new memories.
But here is where the story gets really mind-bending. Henry could still learn new skills. For instance, researchers gave him a tricky task: trace a star while only looking at its reflection in a mirror. And day after day, he got better and better at it. The crazy part? Every single time they gave him the task, he had absolutely no memory of ever having done it before. Think about that. He could learn how to do things, but he couldn't remember that he'd done them.
Henry's case was a total game changer. It proved that memory isn't just one thing. We have at least two completely separate systems working in our heads. The first is declarative memory. That's the what, things you can declare, like facts and events. The second is non-declarative memory. That's the how, the unconscious skills and habits. Henry's declarative system was wiped out, but his non-declarative system was still humming along just fine.
And we use both of these systems all the time. Remembering the capital of France? That's your declarative memory. You have to consciously pull that fact up. But what about tying your shoelaces or riding a bike? You don't even think about it, right? That is your non-declarative system running on autopilot. It's the muscle memory, the habits that work in the background.
Okay, so we have these two distinct memory systems. That brings up the next obvious question, right? Where is all this stuff happening? Let's take a look at the brain's memory map.
Turns out, different parts have different jobs. That hippocampus, the part they took from Henry, it's like a temporary notepad for new facts and events, for our declarative memories. Meanwhile, the basal ganglia is more like a coach, drilling our non-declarative skills and habits into us. Then, once those memories are ready to be stored for the long haul, they get sent out to the cortex, which is like a massive hard drive.
But here's a huge plot twist. The memories you make during the day, they're actually really fragile. The process that makes them stick, that moves them from the notepad to the hard drive, most of that happens when you're not even aware of it. It happens while you're asleep.
And get this, even different parts of your sleep cycle have different jobs. That deep, slow wave sleep you get early in the night, that's when your brain is hard at work filing away the facts, the declarative stuff. But later on during REM sleep, when you're dreaming, that's when your brain is consolidating the skills, the non-declarative memory.
So we know what we learn and where it's stored, but how does it actually happen? Like down at the level of brain cells? The answer is a concept so cool it's basically a biological superpower. It's called plasticity.
But first, we have to bust a huge myth. One study found that a whopping 82% of student teachers believe that when you learn something, you grow new brain cells. I mean, it kind of makes sense, right? But it's almost entirely wrong. For the most part, you're working with the brain cells you've had your whole life.
See, the real magic of learning isn't about adding new parts. It's about changing the connections, the wiring between the parts you already have. Every single time you learn something new, you are literally rewiring your brain.
I love this analogy. Imagine learning something new is like trying to make a path through a thick, overgrown forest. The first time you do it, it's really hard, right? You're pushing branches out of the way, it's slow going. But if you walk that same path the next day, it's a little easier. And if you keep walking that same path day after day, pretty soon you've got a clear, easy-to-follow trail. That trail, that is a strong neural pathway in your brain.
Now, this whole trail-building idea has a scientific name: synaptic plasticity. Synapses are just the tiny little gaps between your brain cells where they talk to each other. And plasticity just means they're changeable. So every time you practice, you are physically strengthening those connections, making that signal travel faster and more efficiently. You are literally remodeling your brain.
Okay, so this is all fascinating stuff, but how can we actually use it?
How do we work with our brain's natural tendencies instead of fighting against them? Let's talk about how to hack this system to learn smarter.
First up is a big one, spaced repetition. Now, if you've ever pulled an all-nighter to cram for a test, you've done the exact opposite of this. Cramming is like trying to clear that forest path in one frantic sprint. Sure, you make a path, but it gets overgrown almost immediately. It's a weak, temporary memory. Instead, by reviewing information at longer and longer intervals, say after 1 day, then 3 days, then a week, you send a powerful signal to your brain. You're basically saying, hey, this is important, keep this trail clear. Every single review makes that neural pathway stronger and more permanent.
This whole technique is designed to fight what scientists call the curve of forgetting. By making your brain work just a little bit to retrieve that memory, right as it's starting to fade, you're actively strengthening it. You're forcing yourself to walk that forest trail one more time, stamping it down for good. All right, strategy number 2 is active elaboration. Passively rereading your notes is like just looking at a map of the forest. To actually learn the path, you got to get in there and walk it yourself. You have to actively wrestle with the material.
So, what does this look like in practice? Well, try explaining the concept to someone else, or connect the new idea to something you already understand really well. Ask yourself questions about it. When you do this, you're not just building one trail in the forest, you're building a whole network of interconnected paths, making that new information way easier to find later.
And that brings us right back to the most crucial strategy of all. Seriously, you have to get quality sleep. You can use all these other techniques perfectly, but if you don't sleep, it's like spending all day clearing a path in the forest only to have a storm wash it away overnight. Sleep isn't optional for learning, it's absolutely essential.
So, the most powerful takeaway from all of this is that your brain isn't fixed. It's not set in stone. It is a dynamic, living thing that is constantly being reshaped by what you do and what you think. It is designed to change. So the question isn't if you can learn something new, it's what new path are you going to start building today?